So we'll just take up thermodynamics. First of all, let us check it out. The details of this, what exactly do we have to study, some formulas which we require, some important definitions which we require as far as thermodynamics is concerned. So first of all, we'll take up some definitions. The first definition we will take up is specific heat. Specific heat capacity, sometimes we term this as specific heat capacity, sometimes simply we write this as specific heat. Now we define this as the amount of heat required. First of all, this is the abbreviation we use, and we defined it as the amount of heat required. Heat required is written as Q per unit mass to increase the temperature of unit mass of a substance through 1 degree Celsius, and that 1 degree Celsius is normally between 14.5 degrees Celsius to 15.5 degrees Celsius. We write the value for specific heat like this. That is the heat required over the amount of mass, whatever we require, into time. Now this has units joule per mole per Kelvin, or sometimes we write this as joule per kilogram per degree Celsius. Both the units are acceptable, but most of the times we write it in this manner. Now when you talk about a gas has two different types of specific heats. The first specific heat is called specific heat at constant pressure, right? And we abbreviate this as CP. Most of the times it is written as molar specific heat. Molar specific heat at constant pressure. And we define this as the amount of heat required to raise the temperature of unit mass of a substance through 1 degree Celsius, and that 1 degree Celsius will be 14.5 degrees Celsius to 15.5 degree Celsius, right? And this will happen when the pressure of the gas remains constant. We also define another one, which is molar specific heat at constant volume. Now when you write this as constant volume, we abbreviate this as CV, and we write this again in this manner: amount of heat required to increase the temperature of 1 mole of a gas through 1 degree Celsius, that is 14.5 degrees Celsius to 15.5 degrees Celsius, and in this case also the volume should remain constant. Units: joule per mole per Kelvin or joule per kilogram per degree Celsius. These are the units of specific heat. And if I need to find out how much is the amount of heat which is required or which can be taken by a particular substance, I will rewrite this expression in this manner, that the amount of heat required is equal to M into C into delta T, that is the change in the temperature. So much heat anybody can be given. If somebody is given heat, some substance is given a heat, this is the amount of heat that particular substance will have. The second thing in thermodynamics which we require is called thermal equilibrium. Now when you talk about thermal equilibrium, thermal here stands for temperature, and equilibrium, basically when you studied the lower chapters, the initial chapters, you studied about equilibrium, that the net force acting on the system is zero, or the net torque acting on the system is zero. Now this is not the way in which we define for this particular chapter, that is thermodynamics. We say that a number of systems are in thermal equilibrium, or two systems are in thermal equilibrium if they have the same temperature. So if two systems have the same temperature, these two systems are said to be in thermal equilibrium. Now this defines temperature. So we say temperature is a fundamental physical quantity which is a necessary and sufficient condition for two systems to be in thermal equilibrium. That means its equality is the necessary and sufficient condition for two systems to be in thermal equilibrium. So that's how we define temperature. Normally we say it's a degree of hotness or coldness, but remember that degree of hotness and coldness is not the right way to say it. Because if you're supposing you put a small copper piece and small wooden piece in the freezer compartment of the refrigerator, and you take them after some time, you will find that the copper piece is much colder than the wooden piece. But remember, they were at the same temperature. So here the senses are not giving us the true picture. So temperature basically is a fundamental physical quantity whose equality is a necessary and sufficient condition for two systems to be in thermal equilibrium. Now based upon this, we come to the first law, the zeroth law of thermodynamics, which is simply in layman language simply says that if A knows B and B knows C, then A and C, they also know each other. This is the basic what we have. Let us have a number of systems together and let us separate these three systems with the help of two different walls. Let us say this is an enclosure. This is system A, this is system B, and let us say this is system C. This is called an adiabatic wall. Adiabatic means there is no exchange of heat between A and B, and this is called a diathermic wall. Diathermic wall means there will be easily transfer of heat from A to C and C to A and B to C and C to B as well. So what happens is heat will be transferred. Transfer of heat will take place amongst these two. And remember, heat always flows from a higher body at a higher temperature to a body at a lower temperature. So whichever is the higher or lower temperature, they will start exchanging heat till they reach thermal equilibrium. That means no more of exchange of heat occurs between A and C and between B and C. Now in this situation, if this adiabatic wall is removed and in place of this adiabatic wall we put a diathermic wall, and in place of this diathermic wall we put a adiabatic wall, so we will have a situation like this. In this situation we will find that there will be no exchange of heat between systems A and B. This is A, this is B. Now this will be the adiabatic wall like this, and this is system C. So there won't be any exchange of heat occurring between A and B. So it simply means that if A is in thermal equilibrium with C and B also is in thermal equilibrium with C, then A and B themselves are also in thermal equilibrium. This becomes the zeroth law of thermodynamics. Remember, in thermodynamics the first law was discovered first, then the second law, then the third law, and this law was discovered last of all. Now since this is the most fundamental of all the laws of thermodynamics, so therefore it was appropriate to name this as the zeroth law of thermodynamics. Certain terms which we use in thermodynamics, we use a term called surroundings, we use a term called system. A thermodynamic system is a system which has certain values of pressure, volume and temperature which may or may not change. If this system is placed somewhere, so whatever is surrounding that term is termed as surroundings. Now there are some thermodynamic variables. Pressure, volume and temperature are termed as thermodynamic variables whose variation causes different thermodynamic processes. We need to understand about the thermodynamic processes. Now what are these thermodynamic processes? There are 4 thermodynamic processes with which we deal, and as far as your CBSE is concerned, we need to work only upon the first and the second one. First is called isothermal, second is called adiabatic, third is called isobaric, and fourth is called isochoric or isovolumic. These are the 4 processes we have, and depending upon what remains constant or what changes in these processes, these have been named. When you talk about an isothermal process, there is no change of temperature. That means delta T is 0. That means temperature remains constant. This is an isothermal process. Then the second process is adiabatic process, in which no exchange of heat takes place. That means Q is constant. Neither heat will enter a system nor heat will leave a system. When you talk about isobaric, then there is no change in pressure. The value of pressure remains constant. Right? And when you talk about isochoric, there is no change in volume. So you can say volume remains constant. Now these are the 4 processes. Normally we show these 4 processes on a diagram. On the y-axis we take pressure, on the x-axis we take volume, and this diagram is termed as the indicator diagram, or it is termed as a PV diagram. Now if you make a PV diagram like this, volume this side, pressure this side, and we start from the same state for all the processes, then these 4 different types of graphs are obtained like this. And as you can see here, if I number these graphs 1, 2, 3 and 4, you will find one thing, that in graph number 2 and 3 there is an increase in volume, and so is there an increase in volume in graph number 1. Now graph number 1 is at a constant pressure, so this is called as isobaric process. Graph number 4 is at a constant volume, so this is termed as isochoric process. Right? And if you look very closely at the remaining two graphs, that is 2 and 3, so they have the different slopes. Slope of 3 is greater than the slope of 2. Now when you talk about these two, then in expansion, this is the isothermal curve, isothermal graph, and in expansion, this is the adiabatic graph. In expansion, so if contraction will take place or compression will take place, this will revert. The upper graph will become adiabatic and the lower graph will become isothermal. Now since in thermodynamics, if you need to find out the work done, we have in thermodynamics work done something like this, which comes down to this particular level. So in thermodynamics, whenever work has to be found out, this is how we find out the small amount of work. And to find out the total amount of work, all we need to do is integrate this particular relation between two sets of volumes, that is volume initial and volume final. Right? Now if I look at this PV graph and if I take the product of pressure and volume here, then the product of pressure and volume simply is the slope. So if I take the slope of graph number 2 or graph number 3, then the slope of the graph will give me the amount of the work done. So not the slope but area. The area under the curve. The area under the curve. Okay, let's see it once again. If I find out the value of work done, then work done will be force into displacement, which is force is basically pressure multiplied by area into displacement. So this gives the small amount of work which will be done in thermodynamics. Now if I integrate this, I'll get the total amount of work done. Now when you come back to this PV graph, if I take the area under the PV graph, the area under the PV curve gives me the value of a product of pressure and volume. So when I talk about the area under the PV curve and talk about the pressure and volume, so area under the PV curve will be equal to the work done by the gas. Now if you move from top to bottom, that there will be an increase in volume, work done is positive. If there will be a decrease in volume, work done will be negative. Right? Okay, moving on further, we have two different types of more processes in addition to these. One is called a cyclic process and the other is called a non-cyclic process. So if I talk about a non-cyclic process is one which will start from a certain point and it will be ending at a certain point. Say it starts from point 1 and ends at point 2. This is called a non-cyclic process. The area under this graph, that is this area which we will highlight here, the area under this graph gives the amount of work done. Now when you talk about the second process, which is called cyclic process, normally what happens when I talk about the section called, the chapter called work, power, energy, in that particular chapter we found that if you body is moving along a circular path, the work done comes out to be 0. But this is not the case in case of thermodynamics. In thermodynamics, if I draw the PV graph for a cyclic process, I will have something like this. Now this is the cyclic process. You are starting from a certain point and ending at a certain point. This is called the cyclic process. That means you start from point 1 and move to point 2 and we are moving in the clockwise direction. Now the area of this curve, the area inside this loop, that gives you the value of work done. So here the work done is not 0 in a cyclic process. The work done is equal to the area of this. Now if this loop is moved clockwise, right, then work done is positive, and if this is moved anti-clockwise, right, then work done is taken as negative. Now if you can see here, we are moving in the clockwise direction in this loop, so the work done will be positive in this particular case. So these are certain things which we need to remember as far as some definitions are concerned. Now moving on further, we will move on to the first law of thermodynamics. Before we move on to the first law of thermodynamics, we need to talk something about internal energy, the abbreviation for internal energy is U. Now when you consider the kinetic energy of all the particles of the medium and the interaction, the potential energy of interaction between them, then the sum of kinetic energy and potential energy of interaction between the various molecules, various particles, that is what we term as internal energy of the system. Right? What needs to be understood here in thermodynamics is that if I consider an ideal gas, if I talk about internal energy, it depends upon a number of factors. But if I consider an ideal gas, then I find out that internal energy is simply a function of the temperature of the gas. What does it mean? It means that if the temperature of the gas is more, the internal energy is more. If the temperature of the gas is less, the internal energy is less. So internal energy changes in accordance with temperature. You increase the internal energy, temperature increases. You decrease the internal energy, temperature decreases, and vice versa. If there is an increase in temperature, there will be increase in the internal energy, and if there is a decrease in temperature, there will be a decrease in the value of internal energy. Now on the basis of this internal energy and on the basis of the amount of heat supplied, we will talk about the first law of thermodynamics. Now this is simply a mathematical law which simply states the law of conservation of energy, that if you add a certain amount of heat to a system, a part of that heat is used by the system to increase its internal energy, and whatever remains is used by the system to do some useful mechanical work. Supposing we supply an amount of energy dQ, sometimes we write this as delta Q, which is much smaller than this, to a system. Out of this, the system utilizes this much to change its internal energy, and what remains is the energy available for doing some useful mechanical work. So whether I write it this way or I write it this way, this is the mathematical form of the first law of thermodynamics. Now since dW can be written as pressure into change in volume, so the amount of heat dQ will be equal to du plus pressure into change in volume, something which we need to remember because a lot of numerical problems are based on this particular segment in your competitive examination. Talk about dQ. So if you talk about the first law, the mathematical form of first law is this. Three terms we see here. We see here the heat supplied, we see here the internal energy, and we see there the work done. Now what is the sign convention we use as far as physics is concerned for thermodynamics for this? Now if you add heat, or we can write this heat added to a system. Now if you add heat to a system, then we will take plus dQ, and heat removed from a system. If you remove heat from a system, we will write this as minus dQ. Now this is the sign convention we will utilize, and you have to be very cautious about this, because when you have some graphical representation, some graphs there or some numericals where it is written that heat is added or heat is subtracted, with the numerical value we'll have to write the negative sign or the positive sign. Talking about internal energy, so increase in internal energy, increase in internal energy. So whenever the internal energy increases, then we will write plus du. And what do you mean by increase in internal energy? So basically we mean that if the temperature of the system increases, then du will be taken as positive. And then if you have decrease in internal energy, if you have decrease in internal energy, then in this particular case, or when the temperature decreases, we will take this as minus du. Talking about the third one, that is the work done. Now this is something which is different from what we teach in chemistry. Work done by the system. By. Now what do you mean by by? By means that the gas expands. System means the gas here, the gas expands. So whenever expansion will take place, that is the gas is expanding, the work is being done by the system. So work done by the system is taken as positive. तो इसको हम बोलेंगे चलेंगे plus dW. Work done by the system will be positive, and work done on. So when do we have the work being done on the system? When we have compression. So work done on the system, that will be taken as negative. That means you write minus dW in this case. So heat added to a system positive, heat removed from a system negative, work, internal energy increase in internal energy positive, decrease in internal energy negative, work done by the system, by means expansion positive, and work done on the system means compression, that will be negative. Now these conventions we have to utilize whenever we have to solve any numerical problem, or whenever we have to talk about some graph from where we are trying to find out the work done, whether it is positive or negative. Now there are two applications of the first law of thermodynamics. The first one is called the Mayer's formula. In Mayer's formula, we simply have to show that Cp minus Cv is equal to R, where Cp is the specific heat at molar specific heat at constant pressure, and Cv is the molar specific heat at constant volume, and the difference has to be shown is equal to R, where R is called the gas constant. It is 8.3. The value of this is 8.3 joule per mole per Kelvin. This is the value of this J, 8.3 joule per mole per Kelvin. This is the standard value we take for 1 mole of a gas, whenever you have talked about 1 mole of a gas. Now supposing we supply heat to a system, let us say, what is that system? So anytime when you have to talk about a system in thermodynamics, the system will be consisting of this arrangement. This is called a piston cylinder arrangement. This is a piston and this is the cylinder. Right? In the piston cylinder arrangement, we will always consider some gas, some idle gas, and probably 1 mole of an idle gas, and heat will be supplied to it. Now let us say we supply some amount of heat to it so that the volume of this gas does not change. That means the volume remains the same. If the volume remains the same, then the entire heat will be utilized by the gas in increasing its internal energy. So therefore, we always write internal energy for n mole of a gas to be this much if dt is the increase in temperature. So this needs to be understood, that internal energy is always n times Cv multiplied by dt. If you consider 1 mole of an ideal gas, so we will simply write this. Now let us suppose that we supply heat to this arrangement at constant pressure. So if the pressure is constant, so obviously when you heat the gas, the volume has to increase, and we'll allow the volume to increase so that the pressure remains the same. In that case, the amount of heat given for n moles of the gas is this, or given for 1 mole of the gas is this. So this is the value of dq. This is equation number 2. Right? Now when the gas expands, what happens? The piston is pushed outwards. When the piston is pushed outwards, some useful work is done, and that useful work is given by this expression. This is equation number 3. Now by the first law of thermodynamics, we have that dq must be equal to du plus dw. So we can have Cp into dt will be equal to Cv into dt plus P times dV. Right? Now since we have temperature in 2 terms and pressure volume on 1 terms, so the ideal gas equation for 1 mole of the gas is this, PV is equal to RT. We'll differentiate this at constant pressure. When you differentiate this as constant pressure, you will get this relation. So Cp into dt will be Cp into dt plus R times dt. So we'll simply have Cp minus Cv is equal to R, and this is called the Mayer's formula, and this is based upon the application of the first law of thermodynamics, something we will use later on. Now since R is positive, so it goes to tell us that Cp is always greater than Cv. Reason is simple, because when you supply heat at a constant volume, only one thing happens, and that is the temperature of the gas increases through a small, say through 1 degree Celsius. When you supply heat at constant pressure, 2 things will happen. Number 1, the temperature of the gas will increase through a temperature of 1 degree Celsius, and at the same time some useful mechanical work will be done. So since heat is required for both of them, so therefore Cp is always greater than Cv. Now moving on to another application, which is Poisson's equation. Now this Poisson's equation is basically an equation of an adiabatic process, and this is that particular equation, that PV to the power gamma is constant. And what is gamma? Value of gamma is Cp divided by Cv, and obviously it is always greater than 1 because Cp is always greater than Cv, so Cp over Cv will be greater than 1. Now how to find out the answer to this, that PV is to the power gamma is equal to constant? We will start with the first law of thermodynamics. This is the first law of thermodynamics. For an adiabatic process, this is 0. So I can write du plus P times dV is equal to 0. And we know the value of du for 1 mole of an ideal gas. This is the value of du. So we can write the expression in this manner. Now you see here, when you look at this particular expression, we find that there is no temperature in this particular expression. So in this equation, we'll try to remove temperature, and keeping in mind that during an adiabatic process, pressure, volume and temperature, all of them change. So what we will do is, for 1 mole of an ideal gas, we will differentiate and write pressure into change in volume plus volume into change in pressure is R multiplied by dt. So the value of dt will be pressure into change in volume plus volume into change in pressure over R. In adiabatic process, everything changes. Pressure, volume, temperature, so we have to differentiate every one of them. Now substituting this value here, so we will get Cv, this will be multiplied by P into dV plus V into dP. We'll divide this by R plus pressure into change in volume will be equal to 0. Writing further, we can write this as Cv into pressure into dV plus Cv into volume into dP plus R into pressure into dV. We can write this as capital P also. Now this will be equal to 0. This term and this term has pressure into dV constant. So Cv plus R we will have here, plus Cv into V times dP will be 0. So Cv plus R is equal to Cp. So pressure into change in volume into Cp plus Cv multiplied by V times dP will be equal to 0. Now since we need only pressure and volume, so we will divide this equation by Cv into Pv to get something like this, Cp over Cv, and this will be dV by V plus dP by P will be equal to 0. Dividing both sides by that expression. Fine. Now we will rewrite this expression. Now this is gamma, and this is dV by V, and this is dP by P is equal to 0. We will integrate. We will integrate both sides to write this as log of V plus log of P is equal to some constant. Or we can write this as log of V to the power gamma plus log of P is equal to some constant, or we can write log of PV to the power gamma is equal to constant. So when you take anti-log of both sides, then this is the final result we will have, and this result is termed as Poisson's equation. And this is the equation of an adiabatic process, where gamma is the ratio of the two specific heats. Now writing this expression further, PV to the power gamma is equal to constant. We can write the expressions for this. Further, let us say that PV is equal to RT. So from here we will get pressure is equal to RT by V, or pressure will be written as RT by V into V to the power gamma is equal to constant. So we'll have TV to the power gamma minus 1 is equal to constant. This is another equation of an adiabatic process. Fine. We can also from here find out the value of volume in terms of pressure, and then we can write this will be pressure into RT over pressure to the power gamma is equal to constant. So we can write T to the power gamma over P to the power gamma minus 1 is equal to constant. This is another equation of an adiabatic process. So PV to the power gamma is 1, then TV to the power gamma minus 1 is another one, T to the power gamma over P to the power gamma minus 1 is another expression for the adiabatic process. Moving on further with this, let us talk in detail about two processes which we have. The first process about which we will talk in detail is isothermal. As we had just mentioned, an isothermal process is one in which the temperature of the system will remain constant. That means there is no increase or decrease in the temperature of the system. That will remain constant whatsoever. Now, what are the conditions which will be satisfied for this process to take place? Number one, it should take place very slowly. The process should take place very slowly, so that whenever there is increase in temperature or decrease in temperature, then with the help of the surroundings, the temperature can be neutralized back to the normal value. So increase also and decrease also. So it has to take place very, very slowly, and the piston cylinder arrangement should be perfectly conducting. They should be perfectly conducting. If these two conditions are satisfied, then we can say that this process of isothermal process can take place. Number one, very, very slowly. Number two, the piston cylinder arrangement should be perfectly conducting. Now, what are the equations? What are the equations of an isothermal process? Number one equation is that dt is equal to 0, or we say du is equal to 0. And number two equation is that temperature is constant. Right? Now, since temperature is constant, that means PV must be equal to constant. This is another relation, because PV is equal to nRT. So if temperature is constant, R is already constant. So pressure into volume will also be a constant. So these are the three equations which we utilize for an isothermal process. If dt is 0, as good as du is equal to 0, temperature is constant, or P multiplied by V, that will be constant. How does the first law of thermodynamics get modified when we apply this first law of thermodynamics to this process? How does it get modified when we apply the first law of thermodynamics to the isothermal process? Now let's write, this is dq is equal to du plus dw. If the process is isothermal, then du will be equal to 0. It means for an isothermal process, this is what happens to the first law of thermodynamics. That means any heat given to the system will simply do some mechanical work. There will be no increase in the internal energy, because there will be no rise in temperature of the system. Now, if you want to do expansion, isothermal expansion, if I want that isothermal expansion should take place, that means dV is positive, it means P into dV is positive, it means work done is positive, it means that the value of dq should also be positive. And under what circumstances, or what is the convention we have used, why and how, or under what circumstances dq should be positive? dq is positive if heat is added to the system. So that means whenever we want isothermal expansion to take place, we must add heat to the system. Without adding heat to the system, we cannot have an isothermal expansion at all. What if isothermal compression takes place? If I talk about isothermal compression, then I will write all these things will be negative. There will be a decrease in the volume, so PdV will be negative, work done will be negative, so the value of dq will also be negative, and in this case we will have to remove heat from the system for this process to take place. So isothermal expansion takes place when heat is added to the system, and isothermal compression will take place when heat is removed from the system. So when you remove heat, we will have compression, isothermal compression. When you add heat, we will have isothermal expansion. Now, what is the work done in an isothermal expansion, or what is the work done during an isothermal process? We start with this expression. dW is pressure into change in volume, and we know that pressure is equal to RT divided by V. So we will write dW is equal to RT divided by V into dV. Now remember, volume is constant here, so we will rewrite this expression. Temperature is constant here, we will rewrite this expression, and to find out the total work done, total isothermal work, we will integrate between limits V1 and V2 RT dV by V, which gives you RT into log of V from V1 to V2. And if I rewrite this expression, I will get R into T log of V2 minus log of V1. So this will be log of V2 minus log of V1, which I can write as R into 2 RT log of V2 over V1, and this is the work done during an isothermal process. Okay, now let's take up the next process, that is the adiabatic process. First of all, what is an adiabatic process? An adiabatic process is one in which there is no exchange of heat between the surroundings and the system, or the system and the surroundings. Heat will not be exchanged. The pressure will change, the volume of the system will change, the temperature of the system will change, but exchange of heat will not be there. Now, what are the conditions which must be satisfied? Number one condition is that the process should take place very, very quickly. If the process takes place very quickly, there is hardly any time for the system and the surroundings to exchange heat. And as a result, the total amount of heat remains the same. And then you talk about the piston cylinder arrangement. The piston and cylinder arrangement should have perfectly insulating walls. That means they should be perfectly insulating. If they are not perfectly insulating, then there will be exchange of heat. So there should not be any exchange of heat for this process to take place. Now, what are the equations of this process? We have already talked about the equation. There is no exchange of heat, or we can say that Q is equal to constant, or we can say PV to the power gamma is equal to constant, or we can say TV to the power gamma minus 1 is equal to constant, or we can say T to the power gamma, P to the power gamma minus 1 is constant. Now, these are the equations we use for an adiabatic process. dQ is equal to 0, or there is no change of heat, Q remains constant. TV to the power gamma is constant, TV to the power gamma minus 1 is constant, T to the power gamma over P to the power gamma minus 1 is constant. These are the equations we use to represent an adiabatic process. Now, how does the first law of thermodynamics get modified when we apply it to the adiabatic process? Now, this is the first law of thermodynamics. dQ is equal to du plus dW. Now, if it is an adiabatic process, this is 0, so I can simply write du will be equal to minus dW. That means if some work is done, then the internal energy decreases. If the system does some work, the internal energy will decrease, right? That is the meaning of this. Now, what happens during adiabatic expansion? So when you have adiabatic expansion, dV is positive, pressure into dV is positive, dW is positive, therefore the value of du will be negative. So whenever adiabatic expansion will take place, du will be negative, and we've already studied that du will be negative if temperature decreases. If temperature decreases, du will be negative here. That means whenever adiabatic expansion will take place, the temperature of the system will decrease, the system will cool down. Now, when you talk about adiabatic compression, for adiabatic compression, we have this to be negative. We have pressure into change in volume to be negative. We have the work done to be negative, and the value of du in that situation will come out to be positive. That means temperature increases. So whenever adiabatic expansion will take place, temperature will decrease, and whenever adiabatic compression will take place, the temperature of the system will increase. So this is what happens to the first law of thermodynamics when we apply it to the adiabatic process. Now, what is the work done? What is the work done during an adiabatic process? To find out the work done, we will write that small work done is pressure into small change in volume. But for an adiabatic process, we have PV to the power gamma is equal to a constant. So from here, if I want to find out the value of pressure, so this is the value of pressure I will have. So dW will be equal to K times dV over V to the power gamma. Now, if I integrate to find out the adiabatic work done, say between volumes V1 and V2, I will write K outside and I will write dV over V to the power gamma. Now let's try to integrate V to the power gamma. So when you integrate x to the power n, it is x to the power n plus 1 over n plus 1. So work done during adiabatic process will be a constant. This will be minus 1 plus 1 minus gamma plus 1 from volume V1 to volume V2. Okay, now we will rewrite this expression like this: K 1 minus gamma. Here I will write V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma, 1 over 1 minus gamma, K times V2 into 1 minus gamma minus K times V2 into 1 minus gamma. So this is V1. But we know that P1 V1 to the power gamma should be equal to P2 V2 to the power gamma should be equal to constant. So K can be replaced by this. So when you replace K, I will write 1 over 1 minus gamma, and here I will write P2 V2 to the power gamma V2 to the power 1 minus gamma, and here I will write P1 V1 to the power gamma V1 to the power 1 minus gamma. That gives me this relation. This will be P2 V2 minus P1 V1. Now for 1 mole of an ideal gas, pressure into volume is R into T. So the work done during an adiabatic process will be 1 over 1 minus gamma R into T1 minus R into T2. So this is T2 and T1, so we'll write T2 here, T1 here, and if I rewrite this, I will rewrite this in this manner: T1 minus T2, taking the negative sign common, and this is the work done during an adiabatic process. And work done during an adiabatic process depends only upon the initial and the final temperatures. Right? R is a constant, gamma is a specific heat of a gas. For different types of gases, the value is different. For a monatomic gas, it has a different value, 1.33. Then we have 1.41, 1.67, and so on for diatomic and triatomic gases. So this is the work done during an adiabatic process. Now moving on the chapter, we will talk about the second law of thermodynamics. The second law of thermodynamics has two statements. One is called the heat engine statement, and the other is called the refrigerator statement, that is Kelvin statement and the Clausius statement. Now what does the heat statement says, or what does the refrigerator statement say? It simply says that it is impossible to extract heat from a body at a lower temperature and supply it to a body at a higher temperature without the help of an external source. Right? Number two, if I talk about another definition, the second definition, that is a heat engine definition, says that we cannot extract a continuous supply of heat from a body and convert this into work. We can extract it only up to the time the body's temperature becomes equal to the temperature of the surrounding. So that means we cannot convert the entire heat energy into mechanical work. This is what we have in the second law of thermodynamics. Now why we had the second law of thermodynamics? Because there were some limitations. To the first law of thermodynamics. What were the limitations? Number one, first law of thermodynamics does not tell us under what condition heat energy is converted into mechanical work. For example, if I rewrite the equation for you, du plus P times dV, then under what condition is this heat energy being converted into mechanical work? For example, if you fire a bullet, the bullet hits a wall, it gives its heat to the wall. Now if you heat that bullet, will the bullet flow back, go back to the gun? The answer is no. So it doesn't tell under what condition that heat energy is converted into mechanical work. Number two, it does not tell us the extent of heat which will be converted into work. How much? 10%, 20%, and so on. It doesn't tell about this also. And third, it doesn't tell us the direction in which the heat flows, whether it flows from lower temperature to a higher temperature or higher temperature to a lower temperature. Because of these limitations, we had the second law of thermodynamics, which says that we cannot derive a continuous supply of work from a body by cooling it to a temperature lower than lowest of its surroundings. This is called the Kelvin statement or heat energy statement. And secondly, we cannot supply heat from a body at a lower temperature to a body at a higher temperature without the help of an external agent. This is the this is the definition, or this is the statement of the Clausius law, or you can say the refrigerator statement, right? Now, based upon this too, we can talk about the heat engine. The heat engine basically consists of a couple of parts. It needs a source, which is normally called a hot reservoir, and this hot reservoir will be at a temperature TH. Then we have a sink, which is called the cold reservoir. Reservoir is an arrangement having a very large quantity. So if you remove or add anything to it, nothing changes. And then we have some working substance. So what does the working substance do? If you draw a block diagram of this, so we have something like this as a block diagram. Right? This is the source, hot reservoir, temperature TH. This is the sink, cold reservoir, temperature TC. This is the engine. Right? So the working substance will extract a certain amount of heat from the source, QH. Convert a part of this into mechanical work, dW, and whatever remains, little bit remains, will be thrown into the sink. That means amount of heat, QH, will be extracted from the source. Small amount of that will be converted into mechanical work, and the remaining QC will be thrown into the sink at a temperature TC. So this is how it works, and time and again the working substance will go to the hot reservoir, do work, throw the heat to the sink, again go. So this is basically a cyclic process. In this cyclic process, since it's a cyclic process, in a cyclic process the value of du is always 0, because when you start from a point and you come back to the same point, the value of temperature will be the same. So there will be no change in internal energy. Since there is no change in internal energy, therefore for a cyclic process we will have dq is equal to dw. So what is the total work done then? Total work done is the amount of heat which we have utilized, that is QH minus QC. So this is the total amount of work done. What is the efficiency of the engine? Efficiency of the engine is the total work done over heat extracted to do work. So this will be QH minus QC over QH, where QH is the heat taken from the source or the hot reservoir, and QC is the heat which is supplied to the sink or given to the cold reservoir. So this is the work done, QH minus QC, and this is the efficiency of a heat engine. Remember, the efficiency will be maximum if the value of QC is equal to 0. The value of QC is never, the value of stop karo. The value of QC is never 0. Now, whenever a heat engine has to be made, then we must ensure that we have got a theoretical ideal heat engine on the basis of which we can make a practical engine. Now, that theoretical engine is the Carnot heat engine, right? And the cycle on which it is based is called the Carnot cycle. Now, the Carnot cycle consists of 4 different steps. That is isothermal expansion, then number 2, adiabatic expansion, number 3, isothermal compression, isothermal compression, and number 4, adiabatic compression. Now these are the 4 steps on which this engine is based. It has the same parts, it has the source, it has the sink, it has the working substance. Now it also has an insulating stand and a piston and cylinder arrangement. The piston cylinder arrangement is such that the base is perfectly conducting and the surfaces of the sides are perfectly insulating. These are the 4 parts. So for the first part, what is done is that the piston cylinder arrangement is taken and it is placed on the heat source. Right? So what happens is that the working substance takes an amount of heat QH and expands from an initial temperature TH to another temperature, that is TH. It expands and moves to this temperature. Right? And an amount of heat QH is taken in by the substance. During this time, the work done during the isothermal process is equal to W1. The heat extracted is QH and the work done is TH log of V2 over V1. We'll assume that at this point pressure is P1, volume is V1. At this point pressure is P2, volume is V2, and so on. After this, we take the piston cylinder arrangement and place it on the insulating stand. When you place it on the insulating stand, the heat which already it possesses will allow it to expand. So when it expands, and when it expands, there will be a decrease in temperature, and this. Now during adiabatic expansion, there is a decrease in the value of heat, and the work done in this case is simply equal to R over gamma minus 1 TH minus TC. Now the piston cylinder arrangement is taken and it is placed on the stand once again, and it is compressed, and an amount of heat QC is lost, temperature remains the same, and the pressure and volume they move to P4 and V4, and the amount of heat which is lost is QC. So the work done will be equal to QC, and it will be equal to R times TC log of V3 over V4. Now the piston cylinder arrangement is taken and compressed. The piston is compressed and the temperature changes from T3, TC and becomes equal to TH, and it becomes the original value from P4, V4, the volume comes back and pressure comes back to P1, V1. The work done in the fourth case is equal to R over gamma minus 1 TH minus TC. Now this is work done on the system, this is work done on the system, this is work done by the system, and this is also the work done by the system. Now this is called the Carnot cycle, consisting of 4 different points. Starting from here, we call it say 1 to 2, then 2 to 3, and then from 3 to 4. The temperatures change, and this is the total amount of work done. Now if I find out the net work done, so net work done will be W1 plus W2 minus W3 minus W4, which will be W1 minus W3, because these two being equal will simply cancel out. So the value of total work done will be R into TH log of V2 over V1 minus R into TC log of V3 over V4. This is the total amount of work done. Now we will rewrite this expression and see what are the values of TC and so on. Let us see. Now if you look at point number 2 and point number 3, these two are at on the same adiabatic curve. So for them, TV to the power gamma must be constant. V to the power gamma, V2 to the power gamma minus 1 should be equal to TC V3 to the power gamma minus 1, because they are on the same adiabatic. Similarly, point number 4 and point number 1 are also on the same adiabatic. So for them also we will have TH V1 to the power gamma minus 1 should be equal to TC V4 to the power gamma minus 1. If I take the ratio of these two, the ratio of these two will come out to be this much. That is V2 over V3. V2 over V1 is equal to V3 over V4. This is what we have from this Carnot cycle. Now if you want to find out the total work done, then the total work done will be R. We can take common. We can write log of V2 over V1, and we can write TH minus TC here. Now what is the efficiency of this Carnot heat engine? Efficiency is the total work done over heat extracted. This is the efficiency. Total work done is R into log of V2 over V1 TH minus TC, and we have to divide this by R into TH log of V2 over V1, which gives you TH minus TC over TH, which gives you 1 minus TC over TH. This gives you the efficiency of the Carnot heat engine. So lower the value of TC, more is the efficiency. higher the value of Tc, lesser is the efficiency. Now for a heat engine, we also found out that this is the value of efficiency, that is 1 minus Qc over QH. This implies that for a Carnot heat engine, this ratio will hold. This is the ratio which will hold for a Carnot heat engine. That means Tc over Th will always be equal to Qc over QH. Moreover, the efficiency will be 100% if Tc is equal to 0 Kelvin, or if the value of Qc is equal to 0. Both of these are practically forbidden by the second law of thermodynamics. So we cannot have 100% efficiency for any type of engine. So if you have two different temperatures between which two engines are working, then the Carnot engine's efficiency is more because it's an ideal heat engine. Now moving on to the last topic of this thermodynamics, we will talk about the refrigerator. A refrigerator basically is a reverse heat engine working in the opposite direction. So we have got a working substance or the compressor. It will extract an amount of heat Qc. It will do so by doing some work, and whatever remaining heat it has, QH, it will reflect it or it will throw it into the source. Source is the surrounding, and the surrounding is at a temperature equal to TH. This is the block diagram of the working of this refrigerator. So the working substance, which is normally freon gas, with the help of the compressor, will extract heat Qc by doing some work using electrical energy, doing some mechanical work, and then after doing, it will be throwing this heat energy. So the working substance, which is freon gas, with the help of a compressor, will extract an amount of heat Qc from the cold reservoir, that is the contents of the refrigerator. In doing so, some electrical energy will be consumed because mechanical work has to be done, and the remaining heat is thrown into the sink, and that sink is the surroundings, that is the atmosphere, and this is how it works. We define coefficient of performance for this refrigerator. The coefficient of performance is what has been extracted and what work we have done to extract it. So we have extracted an amount of heat Qc, that is the output, and we have done work W to extract that heat. So if I rewrite this, I can write this as Qc over QH minus Qc. This is the amount of coefficient of performance. If I rewrite, I can rewrite it in this fashion, Qc minus 1. But since it's a reversible Carnot heat engine, so we will get this particular expression as the efficiency, rather the coefficient of performance, coefficient of performance of a refrigerator. The value of this lies from anywhere between 1 to 6, 1 to 10. It is more than 100%. So this is the refrigerator statement. So this completes the entire chapter, whatever you require as per as your CBSC. Right? Thank you. So I'll